All right, so we're super happy that Akash Issar is going to be presenting his two-way fixed effects with heterogeneous treatment effects paper by Clément Chamartin and Javier Dafoe. I hope I pronounced those names right. If not, I apologize. And so Akash is a PhD student at the Agriculture and Applied Economics Department at University of Georgia. Is that right?
Yes.
Awesome. So I'll pass it over to you, and for questions and comments throughout is fine. So okay. Thanks, Akash.
Thanks, Taylor, and good afternoon to everyone over here. So my name is Akash Issar. I'm from University of Georgia. I'm not the authors of the paper, as it says, but I'm presenting Chez Martin and Dwight Foyle's paper, a seminal paper published recently in AER, but has been as a working paper for quite a number of years, where they're looking at a limitation that has been recently discussed in the two-way fixed effects estimator, where the two-way fixed effects estimator fails in the case of heterogeneous treatment effects. So feel free to, if you have clarifications or questions in between, I'll try to answer as much as my understanding, but feel free. And so let me start off with, as a student, I wanted to first understand, okay, what is essentially a two-way fixed effects estimator? And it was interesting to know, for example, if you have your canonical DID estimator, like a David card application or something in Angrist and Pishke. So here what we are doing is we're moving on to a data structure or matrix where you're observing a person over time or a group over time. So you have this sort of potential outcomes or outcomes of treated units across periods. So especially in this paper, it's the balanced group, but you can also have unbalanced in the other different sorts of paper. So it's sort of like a square matrix where n might be very equivalent or approximate to t units. So in 2004, Bertrand, Duflo, and Mullainathan presented the estimator to a fixed effects estimator, where if you're observing an individual or a group across time and you have this treatment that you're observing across time, how do you estimate a difference in different estimator? So under the common trends assumption, where you believe that the counterfactual outcomes or the alternate situation that would have happened given you were not treated is independent of being treated or not, you could estimate to a fixed effects estimator by simply adding the individual fixed effects and the time fixed effects and our causal parameter, which is beta. Taylor, just let me know, can you see my mouse move? Cool, thank you. So that's simply under very good assumptions, you get your beta causal estimator, which is your standard difference in differences estimator. But however, recently a lot of work has come up, and we've seen this a few months ago since Taylor started this workshop, that we've had Pedro Santana, we've had Goodman Bacon, Jonathan Roth, and future many more coming that are talking about that this canonical estimator two-way fixed effects fails in certain cases. And what's interesting is Guido Imbens has an overview working paper where he's talking about all of these papers. Well, what's interesting is if you don't have constant treatment effects, or if you don't have homogeneous treatment effects, where, let's, for example, if you have returns to schooling, right? The schooling effect might vary across different groups of people, across different time periods. So your treatment effect might not be constant across units or time. So that's where the two-way fixed effects estimator is limited, because what it's capturing is not actually the causal parameter. It's capturing a lot of different groups treated effects. And I'll be more clear about it, but we've seen it in Goodman and Bacon, where we've seen that the two-way decomposition, the two-way fixed effects can be actually decomposed as to different groups of differences and differences weighted by their proportion of people that are getting treated. And so However, Guido Imbens has said that even though two-way fixed effects estimator might not be the best, it has its own flaws, but it is always a good starting point as to measure the baseline or control outcome when N and T are modest. What that just means is when you've got a good modest size of group size and time dimension, you can use two-way fixed effects as a starting point. But it's not flexible when your dimensions increase a lot. So there's a caveat to it. And if you're interested, Guido Imbens has uploaded his lecture that he just recently gave on in Sargon lecture by the Royal Econometric Society, and that's where he talks about all of these papers that are mentioned in these brackets. So just to recall what this two-way fixed effects estimator that we presented is actually giving us, if all the assumptions, the common trends assumption, and everything else is hunky-dory. So what beta essentially is just telling us the differences in the mean outcome of the treated and the control group. So when everything is good, what we have is weights that are associated with these treated units to be positive and same. So everyone's happy, everything is looking good. But what happens is when our assignment to treatment is more general than a block assignment, meaning everyone is not treated at the same time, or everyone is not given the same amount of treatment, or for example, a staggered adoption that we've seen previously, that people are, like, for example, certain states are adopting certain policies at different points of time. And in Chez-Martin's and Doit-Fall's paper, they have a more general assignment, which is a sharp design, where some people are treated at some time, some people are treated at some time, which is different from a staggered. But staggered is what I understand is one part of a sharp design. So when your treatments is more general than a block assignment, your causal parameter is a weighted average of those who are getting treated versus those who are not getting treated. And this is where a lot of papers have realized that the weights associated with these outcomes may not be always positive. And so a lot of work since Goodman-Bacon and recently like Barker, Locker, and Wang, and especially the one that I'm presenting today, are talking about that these weights can become negative. Okay, so if anyone has any questions or clarification, I can go on to an example. Cool. Okay, so as a student, I wanted to actually, rather than delving into the whole algebra and the method of the methodological aspect of the paper, I wanted to understand this paper via an example. So I have this very simple example, and this is actually given on Chez-Martin's blog. So that's from there, that's what I extracted and understood. So let's take a simple data structure where you have two groups. You have zero group and you have group one. And each of the group is observed 3 time periods, 0, 1, and 2. So that's your structure of the data. Now, what you have is a group indicator, because this is only 2 groups, so you have only 1 group dummy that goes into the two-way fixed effects. And then you have the time dummies or the time indicator, 3 time periods, so 2 time indicators. And then column D is just telling you, okay, let's assign group 0 some sort of treatment in time period 2. And let's assign treatment to group 1 in time period 1 and time period 2. So that's the treatment assignment. Now, the columns of delta 1, delta 2, and delta 3 are just 3 different situations that we are going to analyze. The delta 1 is saying, let's assume it's homogeneous treatment effects. So delta 1 is your beta parameter or your treatment effect size. So let's give everyone a constant treatment effect. And this will become very important because we're comparing our canonical to a heterogeneous treatment effect. And then in delta 2 and delta 3, we have 2 different situations where there's heterogeneous treatment effect, and the difference between delta 2 and delta 3 is just we flipped when there's variation in treatment size. And so Y1, Y2, Y3 are just the outcomes generated by these the group dummies, the time dummies, and your treatment assignment. So that's that. And so we can run an OLS on this specification. So this is your two-way fixed effects estimator. Just run your outcome on your constant, on your treatment assignment, on your group dummies, on your time dummies, and an error component. So what this measures is if all the assumptions are valid, our common trends assumption, there is strict exogeneity, our beta FE is treatment effect. However, Chase-Martin and Doitfoil have shown that this beta FE is actually a weighted average of individual group treatment effects. That is, it's a weighted, let's say, for example, if you're taking situation 1, it is the weighted average of being treated in 0-2, being treated in 1-1, and being treated in 1-2. So it's a weighted average of these individual treatment effects, where the weights add up to 1, and each of these deltas are these individual treatment effects. However, what Chase-Martin and Doitfoil have shown is that it may not be the case when you have heterogeneous treatment effect that these weights need not all be positive, and it could arise that they are negative. So using this example, what I will show below is that what we observe is this beta fixed effects is actually a weighted average of positive as well as in negative weights. And why is it negative? The question arises is because in our simple example, our beta fixed effects is an average of the control and the treated. And so let's actually look at the control, the first DID 0, where we are seeing that the group 0 was treated in time period 2. So we're going to look at his outcome difference when going from time period 1 to 2. So, sorry. So the difference in difference is just simply the difference in mean outcomes between going from period 1 to period 2 for group 0 versus comparing them with group 1 at the same transition period of 1 to 2. And what we observe is it's just the treatment effect of group 0 at time period 2 subtracted by this difference in treatment outcome of group 1. And so now what's interesting is if there was homogeneous treatment effect, our delta 1, 2 and delta 1, 1 would just be 1, 1. So they would just cancel out. And all you would have is the difference in difference for group 0 is just his own delta 0, 2. But however, now in situation 2 and situation 3, we do have variation in treatment effect sizes. So what happens is that this last term does not vanish. So this is where the difference in difference our beta fixed effect might not be actually the true or the treatment effect, individual treatment effect size. It could be overpowered by what's happening in this remaining term. So similarly, if we take DID1 in our case, which is just comparing what's happening to treated group compared to the control group. So there, because control group never observed, never had any treatment in going from 0 to 1. So this is just 0. So it's just the exposure that group 1 had going from 0 to 1. So in that case, it's just delta 1, 1. So treatment heterogeneity does not actually impact in this situation. So what's interesting is that once we combine both DID 0 and DID 1, we can actually, sorry, it keeps slipping, sorry. So we can actually estimate the beta fixed effects estimator, or we can also, as Chase-Martin shows in his paper, we can also do a first difference. First difference is just looking at the change in change. So the changes, that is, you just subtract a person's outcome in consecutive period and their treatment assignment. So in our simple case, because we just have 3 periods and 2 groups, beta FD and beta FE are very similar, are exactly the same. And what's interesting is when you have, and this shows us that when you have homogeneous treatment effects, your beta Fe is actually equal to your treatment effect, which is 1. However, when you have heterogeneous effect, you do see a difference from the individual treatment effects. So what's the crux of this this example is that heterogeneity, in this simple example, heterogeneity can actually cause estimates of the average treatment to be negative. And in third, where the situation third, where we just flipped it from 0 to 2, we do observe our beta fixed effects being very different from our homogeneous treatment effect. So what this example just shows is that we have to be careful when we apply two-way fixed effects if there is heterogeneous treatment effect, because our two-way fixed effects estimator need not give us the correct sign or need not give us an opposite sign to what an individual treatment effect might be. And in a general case, beta, Fe, and Fd will not be equal. In here case, it was simple, but and this actually motivates to another thing that Chase-Martin and Deutfall has emphasized, that if you compare beta Fe and beta Fd, that's one way to assess if you've got heterogeneity in your treatment effect. That's a diagnostic test. Just do a t-test of beta Fe and Fd. If you find it to be different, that's one indication that your estimates are subject to heterogeneity. So, and I will talk about that more. Okay, so that it comes to now this question that how do you know if you have a problem in your data set? So this is your true treatment effect, which is just the weighted average of individual treatment effect, right? This is if you have homogeneity, and your true treatment effect would just be a weighted average of all these individual treatment effects. But however, Chase-Martin and Deutfall in the paper show that when you are, even though with a common trends assumption, you might have heterogeneous treatment effect, the estimator is actually weighted by an additional weight. And that's where the negative and the positive come in. And that's what we've seen is this additional weight is what brings about variation in the estimate that is different from the delta TR. Okay. And so, so one thing before I come on to the weights and the methods about it. So just to give a quick summary, that there's a diagnostic test that Chase-Martin and Deutfall recommend, is that beta Fe, and Fd employ different weights. So a necessary condition for these two to equal delta TR is that WGT, or the weights associated with these fixed effects estimator or the first difference estimator, should be uncorrelated with the treatment effect. So one way, and they suggest the one way we can test this is just get beta Fe, get a beta Fd, do a t-test on it and see if they're statistically different. If they are significantly different, then that is a question about whether there's heterogeneity. And then if they are not statistically different, then you can be happy about it. But they have an additional query about, they have an additional test that you can do is, once you generate these weights, the Stata package that is available with Chase-Martin and Deutfall can help you extract these weights too. So once you can regress these weights on the size of the treatment effect, and I will show you an application on how to do this. But if you regress it and if you find it to be significant correlation, then that's another indicator that your beta Fe or beta Fd is statistically different from your treatment effect or your average treatment effect on the treated.
Can I ask a quick question?
Yes.
So in addition to comparing beta Fe and beta Fd, should we run separate, like different cohorts in different regression and see whether the estimates are different? Let's say run cohort 1 and cohort 2 in two separate regression.
And so that's, I think so what you're saying is something like compare cohort 1 with cohort 2.
Yeah, like compare the estimate of cohort 1 with the estimate of cohort 2. And if there are heterogeneity, then that two coefficients should be different.
True, I think so. That's one way that does make sense to me, but if anyone else can jump in, it's good. But what I understand from this is, in this case, what you're doing is you're trying to see whether your parameter, which is your true parameter in this, is it really constant across your treatment, your groups versus your treated group? I think so that makes sense. I don't know if anyone wants to jump in. I think so that's one way we could also assess.
Okay.
Thank you, sorry.
No, no worries, thanks.
Okay. Okay, so one of the solution, just to jump ahead, and the solution to this problem, to this situation where you have heterogeneous treatment effect, is that Shezmata and Deutfoil have proposed an estimator where you account for this sort of heterogeneity. So what they have proposed is, let's actually compare people who are switching, that is people who are joining a treatment group in 2 consecutive time periods, and compare them with some stable group. So if you see their causal parameter, if you look at this messy little sort of algebra written here, what it's just saying is, let's take the group which is actually switching their treatment. So either you're joining or you're leaving, and let's compare them with a certain stable group, which will be your counterfactual. So for example, if you have, let's take 2 consecutive time periods, and if you're joining, you're going from 0 to 1, your stable group that you're comparing to will be everyone who was never treated in those 2 consecutive time periods. And if you are a leaver, if you're going from 1 to 0, then your stable group that you're comparing to is everyone who was treated in that time period. So that's one way that they have proposed an estimator that accounts for this sort of who you are comparing against when you are actually taking out a difference in indifference estimator. So essentially what they propose is there is this DID, the estimator is called DIDM, and it's a weighted average of those who are joining. So plus just, I'll explain it more further down, but plus just means those who are joining the treatment, and negative means those who are leaving. And what this N10T means is that count everyone who is actually going from 0 to 1, who are joining in a particular time period, and this N01 means everyone who is leaving. So you're weighting it by that. And NS is everyone who is in your switching cells. Okay, so what Shezmata and Deutfoil proposes, your DID plus estimator is, take everyone who is going from 0 to 1, find the difference in their outcome, and weight it by how many people are in this cell versus over everyone who is getting treated. And then compare them with people who have the stable group, as I was mentioning, as they term it, is everyone who was untreated in these 2 consecutive time periods, T-1 and T. So, and then get their difference in mean outcome and weighted by the proportion of people that are in that cell. And similarly, if you've got leavers in a particular time cell, you've got 2 consecutive time periods. So what you do is you take everyone who has gone from 1 to 0, and their stable group that who you're comparing against is everyone who was treated in that 2 consecutive time period. Okay, so before I go into an application, any questions, any clarifications? Cool.
Yeah, I actually had a question.
Yes,
I mean,
I'll try to answer it.
yeah, no, sorry. I just want, like, I was wondering if, like, for example, like a couple of weeks ago, we learned that with the bacon decomposition, we also can kind of know when we have like negative weights, right? is there any difference or any situation in which, like, for example, like the one proposed by in this paper, or the bacon decomposition is more efficient, or like kind of like where to choose one or the other? Like, I don't know.
Yeah, I had the same thought as I was going, and I was also trying to compare it with Callaway and Santana's paper, because they also look at heterogeneous timing or variation of something. But comparing with Goodman-Bacon, that's interesting. And what I realized is that, and I might be wrong, but what I understand from Chase-Martin and Deutfall is more general, while Goodman-Bacon is, correct me if I'm wrong, it's like you've got 3 time period, right? You've got 3 time period and you've got 2 groups. You've got someone who gets treated at first, and then someone who gets treated somewhere in between, and then there's a group which is never treated, right? And their application is more towards staggered adoption, if I am correct about that. So what I have understood from Chase-Martin and Deutfall is more general. If you have this sort of a, what they call a sharp design or a general design, where some people might be switching on and then switching off later, and then you have someone who is, like I just said, like someone who is joining a treatment plus, and someone who might be leaving a treatment at that particular time cell. So I get that this is more general. This is more of a general framework than Goodman-Bacon's paper, where it's just analyzing 2 different groups of difference in difference. Yeah.
Just to jump in there, I think that one of the main differences, of course, like here with Deschamps and Duffwell, like they're developing another alternative estimator, and Goodman-Bacon was just about understanding what two-way fixed effects was actually estimating. Like when you run that regression, what do you get? And the package for Deschamps and Duffwell has their two-way fixed effects weights, and they can be negative, but Goodman-Bacon's can't. There are no negative weights in that conception, but essentially the problem still comes from the comparison of the already treated units to the untreated units, or and so you can still end up with these issues. I think we talked a little bit about it with Bacon afterwards about like, should you still be doing these tests? Like we have now, at the time, we didn't really have these alternative estimators, but now we do. So it's not exactly clear that we necessarily have to. We can just jump right to the estimators. But then to contrast this one, the Deschamps-Martin and Duffwell with the Callaway and Santana, when we talked to Pedro about it, he said, we can't really deal with multi-value treatments, and we can't deal with treatments that are turning off and back on. But in this paper, they can kind of deal with those kind of things. So that's kind of one of the benefits of this paper, I think, over everything that we've seen thus far. I just thought it'd be useful to say, and I could be wrong about some of that, but that's kind of what I'm contrasting this paper with those ones we've seen so far.
Oh, can I just add something? I think it's a really good point. I was just reading the Sun and Abraham, which I think is more like a special case of the Callaway and Santana, and what they talk about with the they require the Sun and Abraham, they have the irreversible treatment, but what they say is sometimes it's going to depend upon your context, that you can think about you can force something to be an absorbing treatment. Like they have an example of like a hurricane, and like the hurricane happens once, but maybe the effects are lingering. So it kind of almost seems like it's research question specific. Like if you can think about your treatment as something that is irreversible, even if it technically turns on and off, I think that there's sort of that nuance to it as well. So just another thought, I guess.
That's a great point. Thank you. So just to like add on to that, but I did like, there is this, I forgot his name, but Taylor can correct me. There is this sort of this app, the Shiny app that is available where you can actually compare, I forgot the author's name, I'm so sorry. His sweet SV, it starts with SV, I forgot his name. But he has the Shiny app where you can actually compare this Chase-Martin's estimator with the Goodman-Bacon, and I think so. What I saw was that it's only in a very short dimension of like two group, or not two groups, but if you have like 3 time periods, or if you just have these particular 2 groups of people getting treated versus untreated and their treatment remaining same all across, you get somewhat similar results. But that's what I understood from Shays Martin is more general, because you might have a general design of a treatment. Okay. You might have more general design of how you're assigning treatment if you're getting, do I have a question or someone saying something? Cool. Okay. So yeah, I was just saying that there is what I understood was that Shays Martin and Dortfeld is more general, and you have more of a sharp design or a general design where you need not have staggered. Staggered adoption is one subset of the design, but you could have this sort of someone switching on a treatment and someone going off a treatment in this case. Okay, so before I wanted to, since I have about a bit less than 30 minutes, I wanted to actually like explore this method via their application that they have also shown in the paper, where they've looked at the effect of newspaper circulation on voters turnout during a presidential election. So what they've done is they have taken the data set from Genskow, Shapiro, and Sinkinson. And what they've done is where they examine how newspaper circulation or how the spread of the newspaper impacts presidential election voting turnout between 1868 to 1928. Now, what's interesting is I'll leave this to Taylor to explain, but in this sort of application, because the treatment is not binary, here you have the number of newspapers that are circulated. They employ a more fuzzy difference in difference estimator. It's available, but since this is a non-binary treatment, they use a fuzzy DID Stata package, and that's coming on later down the months when to explain it. Okay, so simple is that Genskow, Shapiro, and Sinkinson, what they do is they run a first difference estimator. So what you're just doing is you're taking the first difference of people's turnout between the presidential elections, T and T minus 1 in a particular county. And they run it on a constant and a state year fixed effects. And here state year is not individual state year fixed effects, it's a interaction between state and year fixed effects. And plus a first difference of the newspaper count in a particular county. And so what Genskow, Shapiro, and Sinkinson find is that if you increase a newspaper count by 0 from 1 to 2, or an additional newspaper circulation, presidential turnout increases by 0.26 percentage points, with the mean being about 65%. So what Shays Martin and Dortfeld do is, okay, they use this data set and now apply their estimator to this particular situation. And so not only do they estimate the beta first difference as they find it's 0.0026 or 0.26 percentage points, but they also calculate the fixed effects estimator. And here we find an interesting aspect. We find that beta fixed effects is actually negative. And if we compare beta FD, run a t-test on both of them, they're statistically different. So we can conclude that there is this heterogeneity in the treatment effects. And so, so then they say, okay, let's run our estimator. And what they find is about 4.43 percentage points, which is higher than the beta, what Genskow found. And if you do a t-test, it's statistically different. So their estimator is of the correct sign that newspaper circulation does increase voter turnout, but they find effects to be larger. And another thing that the paper contributes is that if you are very skeptical about the common trends assumption that they have, is that if you believe that the potential outcomes for the control group or the treated group is independent of any sequence of treatment, then you can also run a placebo estimator. And they provide this in their package, where what you're doing is you're comparing 2 periods lags. you take 2 periods before and see if there was any difference in timing, difference in outcome between the treated and the control group 2 periods ago. And the hypothesis is that if common trends holds, then the expected effect should be 0. And that means, okay, we do not need to be worried about the common trends being violated. And so that's why they run this placebo estimator in their package. You can also run. And what they find is if you take the t-test, it is insignificant. So the common trends assumption is satisfied in this case. And this last column is just saying, okay, because we are running 2-period lags, we are losing certain observations. So let's run our own estimator on this placebo sample. And they find the estimate very close to what they found in their overall population. So they're happy. They're like, okay, it's good. Everything is well. So another thing, so just to come on to the aspect about it, if as researchers, we are planning to use it, so then we can run a diagnostic test that I had mentioned a couple of slides ago, just compare beta FD with FE. What they found is that T-stat was significant, so you reject it, and you reject the null hypothesis. And so what they say is that beta FD and beta FD is a biased estimator of the average treatment effect on the treated. So it makes you then ponder, okay, there are negative weights happening, find out how many weights there are. One thing, if you read the paper, it's interesting is that in this package that they have, a two-way fixed, DID multiple G, something of that sort, and fuzzy DID, you can also extract these weights. And one of the things you can also provide in your descriptive statistics is that what is the proportion of negative weights to the positive weights, and the sum of the negative weights if it's contaminating your positive weights, and you can all figure that out. It's quite interesting. And then further, again, there was this other diagnostic test, which I was mentioning, is that, okay, you extract these weights and then run these weights on the size of the treatment effect. Now, size of the treatment effect is unobserved. So what they do in this case is they run this regression of the weights on a proxy for the size of the treatment effect using the year dummies. Now, why they do it is because you have to have a reasoning behind it. So the theoretical reasoning behind is that the circulation of the newspaper varies by time, by county and time. So what they want to see is whether these weights are correlated with your treatment effect. And for that proxy, they're using the time. And what they find is, if anyone's interested, the Stata package is two-way FE weights. And so the outcome is your presidential turnout. This is your group dummy indicator. This is your time dummies. And this is your number of newspapers that are circulated. You are telling the two-way fixed effects package that you want to get the fixed effects estimator. You can also run another one and get the first difference estimator. You tell your controls, which is the state year time, state year fixed effects. And you have, and since this is running on Bootstrap, you can tell it how many bootstraps to run. And if you've got a cluster, here the cluster was county. So you have a blocked bootstrap that is running 100 times. And then the option is that you want to test whether these weights are uncorrelated with your treatment effect. And so what you give the option is that test random weights and tell which variable you're proxying it with. So that's here. So interestingly, the results of the estimation is that if you run a first difference, you get negative weights and it's statistically significant. And what this tells us is that it is correlated with the treatment effect, the size of the treatment effect, and it might be causing our first difference estimator, or the first fixed effects estimator, two-way fixed effects estimator, to be biased from the average treatment effect on the treated. So it's one diagnostic, and if you run a fixed effects estimator, which is this one, that is statistically insignificant, and in that case, you're getting, okay, everything is fine. So there are both these diagnostic tests to do, and then make your conclusion about, okay, what is worrisome for you. Yeah. Okay. So if given, let me try to just like conclude with a little bit that if you have the common trends assumption, fixed effects and first difference regressions identify a weighted sum of the average treatment effect. But these weights, as we've seen, can be these weights can be estimated, and they're often negative. And when you have these negative effects, your beta FE or beta FD might not be the true average treatment effect on the treated, even though your individual effects, as I showed in that simple example, was positive, but your beta fixed effects might not be positive. So, and what Shizmata and Dodd-Foyle have done is they've proposed an alternative estimator, which is robust. And their applications show that if you use a fixed effects estimator first difference or their estimator, there's a lot of difference in what you observe. So I think so I'll end with that. And if anyone has questions, jump in, and everyone can jump in. Yeah. Okay.
Thanks, Akash.
Yeah, thank you.
I think that since we've had John Roth presenting, we would be remiss not to mention, oh, there's a perfect slide for this, that anytime we're talking about these placebo kind of tests, that we should be thinking potentially about the power of these tests and maybe using the tools that he and Ashish Ramachan have developed for some of this testing, for some of these testing purposes. And so when he was presenting, he said, oh, you can basically port in any kind of output from a different estimator. So you mentioned Callaway and Santana, but there's really no reason you couldn't also potentially use this for that as well. So I think it might be important that we mention that as well.
It's interesting, and I was looking at like people who have cited this Shizmata and Dodd-Foyle, and it's quite a lot. And people are like, for example, I attended one of the seminar which was looking at domestic violence during the COVID lockdown, and so you want to see and they tested for these negative weights, and they find a very small number of negative weights. So they're like, okay, we are fine. So, but they use this sort of, I think so it's this estimator, two-way fixed effects, which will help you figure out, okay, you've got weights, how many weights are negative, and you can, if getting negative weights is really, contaminating your results. It's quite interesting.
I think one of the challenges here, when I read this, when I started playing around with it, is that it's not exactly clear what it means to have too many, like what proportion of our weights should be positive. It's not exactly clear, and at what point it really does start to impact the results, because you can have some of the signs flipping even with under 30% of the weights being, for example, or things like that. So it's not entirely clear, and I believe they do have some guidance, but it is kind of just like use your best judgment, I think. Yeah. is kind of what it boils down to. So again, that kind of brings you back to the thing we were talking about before, or the question we were talking about before, which is, now that we have this wide array of alternative methods with stack data, and then the two-stage and this one, and the Callaway and Santana, now that we have all these different estimators, do we really need to run these weights and look at them first? It's not.
Or do you just run the DIDM?
Yeah, I'm not sure exactly what to do. I mean, certainly some of these are a little bit slower than just running a two-way fixed effects estimator, especially if you have a lot of data. But I'm not sure exactly what. It just seems like it would be potentially more work to run a two-way fixed effect estimator normally, and then check the weights, and then try and figure out, okay, do I think this is actually affected, instead of just initially running one of the alternative estimators. So I'm not 100% clear on what to do there. I just thought I'd mention it.
Yeah. So if you all get a chance to watch the Sargon lecture by Guido Imbens, he actually, he just gives an overview of, we are working in panel data, and we want to have a causal framework. So difference in differences, this two-way fixed effects is one of the aspects, but you also have the synthetic control designs that you can also do. But he gives an overview, but he's talking about, the main focus is how do you measure your counterfactual or your potential outcome, because you don't observe it. So you have this sort of, in this case, what we are doing is we are looking at switching cells. That's what I was able to get. Like, okay, you're looking at 2 consecutive time periods, you've got switching cells, and you're comparing it with everyone who is stable. And how what Chez Martin calls stable is that if you've got a joiner, everyone who is untreated is stable. And if you've got a lever, then everyone who was treated is stable. What's interesting is what Guido Imbens is recently developing in his new framework is another way to figure out this counterfactual treatment of who you're comparing against. And it's right now I'm still trying to figure out it. They call it the matrix completion method, which is interesting, which just means is you're trying to fill in those, puzzles or the pieces. You're trying to figure out, and they use some low rank matrix sort of thing, but you're trying to figure out who your Y0 is, what your Y0 would have been. And it all boils down to that. And it's interesting to learn, like now, when I was reading this paper, comparing with the other literature, it's all about what your counterfactual treatment is and how accurate your measure is. So some people use synthetic control. If you've got a tall data structure where you've got a large number of ends and very few time periods, so they'll use I think so. That's where you use synthetic control, or if you've got a very fat matrix, then also you can use some sort of another counterfactual treatment. But it's interesting. Yeah. So I remember it's just to the one more thing, like Anne had that question about what if we just run the treatment and the control group. I was wondering if anyone has any thoughts on that, separate regressions on that.
I think in a way it's a Fedler-Nielsen approach. I think it's just another way to do it. And I agree with what Taylor was saying. I mean, when I read Sun and Abraham, the way I understand it, that even without heterogeneity treatment effect, like this paper pointed out, the weight can still be wrong. So I think maybe this paper or other paper was like maybe they will have to convince people that why the two-way fixed effect is not the best way to go, and maybe that is why it's coming to whole testing. But I think now, since a lot of people kind of agree on that ground, then maybe now we don't have to test, but use the new method that they propose. Yeah, anyhow.
Yeah, no, that's pretty interesting. Because so what I gather is like, since I'm also foraying into difference in difference, and it's interesting is that, okay, you have 2004 two-way fixed effects estimator. The common assumption is, okay, you have a homogeneous treatment effect, right? And then now you're coming on to where people are figuring out, okay, this sort of treatment effect could vary across time. And essentially, I think so now even people are working on, the dose response, dose response could differ across different groups and different time. And in this case, what it was is the treatment is still binary. Everyone gets treated. It's just the size of the treatment is varying across groups and time. So I think so what I could gather is, okay, let's take this example of a voter turnout, or the other example that he has in his paper is the union membership on log wages. I think so it comes down to your application, and do you believe whether your causal parameter, your difference in difference parameter actually varies across groups and time, and then start building up onto that. It's quite interesting, yeah.
I know that, so for the multi-value treatment and things like that, they have a new paper on that, and that's what is going to be presented later on in the summer. So if anyone's interested in that stuff, then there's definitely going to be more coming on that, because this paper doesn't really delve into that too much in thinking about that. But yeah, that's definitely coming up. For the I think for like if you were to run it on 2 different cohorts and then see if those effects are different, I think ultimately it's the I'm a little worried that like you still have the same problems in the estimation strategy. So it's not clear that if the counterfactual groups are changing simply by the variation in when things are treated, and we saw that also matters where in the sample or when in the sample you're treated, which like if you're treated more in the middle of the sample, then you're upweighted, the variance is upweighted. We saw from Good and Bacon. So like even if you estimate it separately for different cohorts and then compare to see if those effects are different, I still think that you would still potentially have a problem. And I'm not sure that that would get you all that much useful information about the presence of those heterogeneous treatment effects if you can't exactly trust the estimates.
Can we
You're
use
just
the
using
same?
regular
Can we use the
effects.
same counterfactual though? Like, why do you need to use a different counterfactual? I mean, Fedler-Nielsen use a different counterfactual, but then you can always change your counterfactual if you have a never treated group, and that would be kind of your base group.
If you have a never treated group, then I think that makes a lot more sense. If you're in like a staggered adoption setting, I think that then that becomes definitely more tenuous to think about for sure. I think the never treated is good there. And then the potential concern when you have the never treated group is that you might have factors that are
Right, parallel trend.
that are selecting into, you might have violations of parallel trend because of the factors that are leading to the adoption of the treatment in the first place. And if you were to just use the staggered adoption variation, then because everyone is eventually adopting the treatment, then that may be like getting rid of the selection into the treatment because everyone is eventually treated. So it's probably more plausible that these units are more alike. And so ultimately, I guess the difference is just the population that you're making inference on.
No, true.
And just to add on that, and this is what I've gathered is, and I was just saying a few minutes ago, it's about who you're comparing your counterfactual to. So I think so with Callaway and Santana's paper, it's okay, you take the control group and you impute the fixed effects and the time fixed effects from the control group and then get your tau hat, which is your causal parameter. And all of this now, like even with Martin's paper, it's like, if you've got people, who are you comparing against? And that's what I understand. And if you've got people you're comparing against who've already been treated, so now they're still receiving the treatment. So what's happening is if in a particular group and time cell, if your comparison group has been already been treated, so you're getting sort of this contaminated results in this period, and that could generate these negative weights. And so what they have proposed is that, okay, let's just take people who have switched and then compare it with people who have not switched. And if they're switching, yeah, that's what they're doing. And I think so there are different, like as I had shown in the literature, that there are these different other papers that are coming with different ways to account for this sort of heterogeneity in your treatment effects. It would be interesting to see further papers how they are dealing with this sort of heterogeneous treatment effects that is different from Martin's.
I have a question for you guys. So for the estimator, when you have levers, like like the thing we have in the slide, imagine like this is probably like a common case. Imagine you have like the effect for joining the treatment is positive, but the one for leaving the treatment is negative. So when you estimate this aggregate effect across both groups, probably your effect is gonna like turn towards zero, right? So I was thinking how this aggregates like on an event study and how that would affect the effect you're getting from this estimator. So maybe under those settings, it's more useful to like compute separately its effect, like from leaving and joining. I don't know if you have any comments on that or any thoughts.
So I think so. What you're asking is that, is it possible that these become negative? Is that correct?
Or even zero, like canceling them out, like.
So interestingly, he does mention that in his paper that you could have this did plus t could be 0 when what you're comparing, if you've got a switcher, but what you've compared is there's no 1, right? Let me correct that. I think so. Yeah, so essentially it could be 0 because you could have groups that have never switched in a particular cell, or so you could land up, but the point is that if you are going from, let's say you're going from, and I'm just thinking this in my head right now, like if you're going from a lever, that means if you're turning off the treatment, so then you would have an outcome that would come over here, but interestingly, I think so it'll still be positive because you'll have people who have been treated and they're still getting some sort of positive treatment, but that might be less, but they're still experiencing some sort of a positive treatment, and that's what outweighs whatever's happening to a switcher or lever. And that's what I think so is, I mean, when he's conducting his DIDM estimator and you are getting the correct sign, which just means is that the true effect is actually positive. And I think so I'm messing this up. If anyone has anything to say, good.
Off the top of my head, I don't know whether or not like countervailing, if you had countervailing ATTs on subgroups, if that would just be, if that could lead to like an AT for the combined of 0. My intuition is that probably could be the case if you had that. But I don't know for sure. That's something that we can email Clement about that, which is I think that's the underlying question there. As for the question about like, should you estimate them separately, like the joining and the leaving? I think it's possible. I think that Pedro mentioned that. Did Pedro mention that, or was it Bacon who mentioned that might be something to do, is to estimate them separately? But then you still have to make a decision about what pretreatment to include, I guess, for the, like how far back to go for your pre-treatment period for the people who are leaving. I think that's something that you can potentially do, just include all of these at once. And I think that that's something that maybe, I think Kamal touches on in another one of the papers with Upwell. They have a lot, so that's something that we can definitely ask as well. But I think that estimating them separately is one possible strategy to do to see if there are differences. Like you might be interested in whether or not the effects of joining and leaving are symmetric, right? And it might not be clear that that's the case from one regression that includes both of these. So you might be interested in that. I think that might be something that you could do. So I'm going to take this opportunity again to thank Akash for the presentation. You did a great job.
I'm sorry I wasn't able to address all of the questions, but thank you.
I mean,
but it helps me prepare for future.
I don't have the coding segment for this week, but what I am planning to do is later on in the summer is to take the coding segments that we've done and redo them and then post them as videos on YouTube that might be about 10 minutes long, or I mean, hopefully, probably will be longer than that, but to do something like that, so then everyone will be able to follow along if just reading the documentation and the code might not be clear. So I'm hoping to do that, and then there'll be one for this as well. So that's the plan anyways. So there's no coding segment for after this one, but I'm probably going to stick around if anyone wants to chat more about this paper. So thanks again for showing up, everybody, and we'll see you again next week for Kurobosiak's presentation.